Alright, hi you guys. So unfortunately I'm not feeling so well, but I wanted to finish your 1.5 lesson on one-to-one functions and inverse functions. In both classes we got through talking about one-to-one functions, so determining algebraically and graphically whether or not a function is one-to-one. Remember, graphically it needs to pass the horizontal line test. In one of the classes I got a little bit farther than the other, but that's okay. I'm just going to start from inverse functions, okay? So an inverse function is a function that reverses another function. So if we have our function f, and f is mapping x to y, then that means the inverse function of f, which we call f inverse, would be mapping y back to x. And I like to show the picture that Algebra 1 teachers always use for whenever they start teaching functions. They make the function machine. So let's say that this is the function f, and that this is just the function that is also the inverse of our function f. So I'll name that f inverse, and they look kind of like candy, but they're my function machines. So if I were to say input 2 into my function f and the output is 4. If I take 4 and input it into f inverse will then spit out a 2. So if f maps x to y, then f inverse will take that same y value and map it back to x. Okay, so if, let's say the functions f and g are two one-to-one functions that are inverses of each other, then these two statements will be true. So f composed with g will be equal to x for every x in the domain of g. And that's because you're evaluating the function f at all of the y values of its inverse, which is the function g. So then if we're evaluating the function f at the y values of its inverse, that should simplify down to x, right? The x values of the inverse for every x in the domain of g. And then it should go both ways. So then g composed with f of x should also be equal to x, but for every x in the domain of f. So this is one way that we can prove that whether or not two given functions are inverses of each other. Just super important to remember, you guys, this is not an exponent, it's a notation. So if you see f inverse, that is not equal to 1 over f of x. Okay, this is not an exponent, it's just a notation for f inverse. Okay, so because inverse functions end up reversing each other, the range of the function is the domain of the inverse, and the range of the inverse is the domain of the function. So they flip-flop. So remember my function picture, all of the inputs for the function f are going to be outputs for the function f inverse, and all of the outputs for the function f will be the inputs for f inverse. So essentially, the domain and range of the function f flip-flop, so that the range of the function f will be the domain of f inverse, and the domain of the function f will be the range of f inverse. Okay, so we're just going to start by practicing verifying whether or not two functions are inverses of each other. So we have to show it both ways. So first I'm going to compose f with f inverse. So f is the outside function. Remember, we practiced this in section 1.4. So f is the outside function. And I'm going to substitute f inverse in for x. So I'm evaluating the function f at f inverse. Now the domain of both these functions, these are both linear functions, the domain is all real numbers, so this is going to be true for all, needs to be true for all real numbers. So we can simplify. Okay, so we'll end up with 3x over 3, which is equal to x. Okay, now we need to show it the other way, so f inverse composed with f. Okay, so f inverse being the outside function, and substituting in f. Okay, so these 3's will cancel. We're left with x minus 2 plus 2 equals to x. Okay, so f composed with f inverse is equal to x for all real numbers, and f inverse composed with f is equal to x for all real numbers. Therefore, these two functions are actually inverses of each other. We just proved that. Okay, let's do that one more time. And now these functions have domain restrictions. Notice that f is 2 minus x squared. Well, 2 minus x squared is a quadratic, and we talked about when we were talking about one-to-one functions, over the implicit, the function f's implicit domain, f would not be a one-to-one function. However, because we have this comma x greater than or equal to 0, we're restricting the implicit domain of f so that it's forcing f to be a one-to-one function. So these could be inverses of each other. So let's do f composed with f inverse again first. Okay, so 2 minus, okay, f being our outside function, we're going to substitute in f inverse. Okay, so this needs to simplify down to be equal to x for this domain, so the domain of the inside function. So for x less than or equal to 2, this needs to simplify down to x. Okay, so let's look at this. So the square root of 2 minus x squared will just be 2 minus x, and I use the parentheses because now I need to distribute that negative. And we get equals to x, and this is true for x less than or equal to 2. Okay, so now f inverse composed with f. So f inverse being the outside function. Okay, so now for these two functions to actually be inverses of each other, this needs to simplify down to be equal to x for x greater than or equal to 0, because that's the domain of our inside function f. Okay, now we get down to the square root of x squared. Okay, you guys know that we would normally, if this were for all real numbers, we would actually have to simplify this to say it's equal to the absolute value of x, okay? Because x can be a positive or negative number, and we can still have real outputs here. But however, with the rules of exponents, when we raise a power to a power, we multiply the exponent, so x would only be raised to an exponent of 1. Now, we don't want the this to be equal to the absolute value of x, because that's saying that's not saying that our function f is a one-to-one function. So this is going to simplify just to x, and I have to say for x greater than or equal to 0. So for the domain of the inside function f. Okay, so these two functions are inverses of each other, but super important that we have this domain restriction here to make this a one-to-one function. Okay, so we talked about how the domain and ranges of two inverse functions kind of flip-flop. So the graphs of two functions that are inverses of each other are going to be reflections of each other about the line y equals to x. And this is because if we have the point b comma a on the graph of the inverse function, okay, then I know the point, or another point, that will be on the graph of f, the point AB, because the x and the y values will flip-flop. The domain and the range flip-flop. So if you know a point on one, either the inverse function or the function, okay, so a function or its inverse, then you know a point on the inverse function. Okay, so if we have this graph, let me identify a few points on here. So this would be the point 0, 5. Where else? We have the point 2, 0, and we have the point 4, -3. Okay, so knowing those points, I can sketch the graph. So let's call this the graph of f. So knowing those points, I can sketch the graph of f inverse. Okay, so if I know the point 0, 5 lies on the graph of f, then I know the point 5, 0 must lie on the graph of f inverse. If the point 2, 0 lies on the graph of f, then 0, 2 must lie on the graph of f inverse. If I know 4, 3 on the graph of f, then -3, 4 must lie on the graph of f inverse. Okay, so then if I connect those points, okay. Writer, I apologize for my shaky lines. Okay, so we have the graph of f inverse. Okay, and you can see that f inverse is a reflection of the graph of f about the line y equals to x. Okay, so to find the inverse of a function, so you're given a function. Okay, first of all, you want to verify that it is a one-to-one function. You can do that just by sketching the graph and verifying that the graph passes the horizontal line test, or you can do it algebraically. I usually just sketch the graph though. Then we're going to interchange x and y, and you're going to solve for y in terms of x, okay? And then whatever we get y equal to is going to be our inverse function. And it's super important to state any domain restrictions on the inverse function. So what I like to do is when I first look at the function that I'm given, if I'm being asked to find the inverse, is to also state the domain and range of this function, because then it's easy to see what the domain and range will be of f inverse. Okay, so x cubed minus 1. Thinking about the graph of x cubed minus 1, that's x cubed being shifted down 1 unit. Okay, would definitely pass the horizontal line test, making it a one-to-one function. Okay, so we're good. So I'm going to rewrite this as y equals to x cubed minus 1 instead of using the function notation. So now I want to try and find the inverse. Now that I know it's a one-to-one function, I'm going to switch the x and the y value. Do that over here. So I'll have x is equal to y cubed minus 1. And I want to solve for y now. So if I add 1 to each side of the equation, I'll have x plus 1 equals to y cubed. And now to isolate y, I can take the cube root of each side of the equation. Okay, so f inverse is going to be the cube root of x plus 1. Oops, I forgot to state the domain and range here. Well, the domain and range of x cubed minus 1, it being a polynomial function, is just going to be all real numbers. Which means that the domain and range for f inverse will also be all real numbers. Okay, so our function f of x equals to the square root of x minus 1. I'm just going to do a quick sketch. So that's the square root of x shifted to the right 1 unit. Okay, one-to-one function, it would pass the horizontal line test. Okay, so I'm going to write this as y equals the square root of x minus 1. Remembering to state the domain and range first. So the domain, x minus 1, has to be greater than or equal to 0. So x has to be greater than or equal to 1. We can also see that from the graph here. And the range we can also see from the graph as 0 to positive infinity. So I can already see what the range, the domain and the range will be for the inverse function. So now to find the inverse function, I'm going to switch x and y. Okay, so first I'm going to square both sides to get rid of the radical. So we'll have x squared equals to y minus 1. And I'm adding 1 to each side of the equation. Okay, notice that f inverse is a quadratic, right? The graph of a quadratic is a parabola. I know a parabola does not pass the horizontal line test, but think about what's the domain here. We need to state the domain to show that this is a one-to-one function. So the domain of f inverse will be x greater than or equal to 0. So that's how we have to state it. We have to state the domain explicitly for this function to show that it's one-to-one. Okay, and now in interval notation, the domain will be 0 to infinity, and the range will be 1 to positive infinity. Okay, next function, 1 over x minus 2. So that's 1 over x shifted right 2. There is a vertical, a horizontal asymptote, and okay, so there's a rough sketch of that graph. Passes the horizontal line test, 1-to-1. So y equals to 1 over x minus 2. Domain, okay, I can see is negative infinity to 2, union 2 to infinity. And the range is, remember, read bottom to top, so negative infinity to 0, union 0 to positive infinity. Okay, so going to find our inverse function, I'm going to switch x and y. Okay, I need to get y out of the denominator because remember, now we're solving for y to find the inverse. So I'm going to multiply both sides of the equation by y minus 2. Make sure you're using your parentheses. Okay, so that'll make this y minus 2 cancel. So I'm left with y minus 2 times x equals to 1. Now I'm going to divide by x on both sides of the equation, so I'll have y minus 2 equals to 1 over x, and I can add 2 to each side of the equation. Oops, that is not a 2, this is an x. Okay, so f inverse is 1 over x plus 2. So same parent function for both these functions. The inverse is going up 2, and the original function we were given is going to the right 2. Okay, domain will be negative infinity to 0, union 0 to infinity, and looking at that function, that makes sense. And then so does the range. Since we have a vertical shift, that means the horizontal asymptote that goes along with 1 over x is being shifted up 2 units. Done. Okay, so now we're going to talk about finding an inverse of a piecewise defined function. So same first step. We need to verify that this is a one-to-one function. So I'm just going to sketch the graph. And I think that's also helpful with thinking about the domain and the range of the function, especially for a piecewise. So for x strictly less than 0, the graph will look like x squared. Okay, notice my open circle. Notice for this part too that the y values are y strictly greater than 0. Okay, then for x greater than or equal to 0, the graph will look like y equals to negative x. Okay, so this is y less than or equal to 0 for that part. So we're actually going to find the inverse of each part, or each piece of the piecewise function, to find the entire inverse of the piecewise function. So for this first part, I'm going to switch the x and the y. Okay, and to solve for y, I'm going to have to take the square root on both sides. We'll have plus or minus the square root of x is equal to y. And we can't have plus or minus. It has to be one or the other. Now, for the piece of the inverse function here, I know that x will have to be strictly greater than 0 and y will have to be strictly less than 0, because these two flip-flop, these two intervals flip-flop, okay, the domain and the range switch for the inverse. So I have to think about for which of these, plus or minus, would this be true? So for y values to be, both would have x greater than 0, okay, that's fine. But for y strictly less than 0, it's actually going to be the negative, okay, so I can get rid of the plus. Okay, so then for the second part, it's pretty easy, so switching the x and the y. Okay, so we just get y equals to negative x again. This is going to be for x less than or equal to 0 and y greater than or equal to 0. So f inverse will be equal to the negative square root of x for x greater than 0, and then negative x for x less than or equal to 0. The domain and range of f is all real numbers, so the domain and range of f inverse will also be all real numbers. And we can confirm that our graph, or I'm sorry, that this is the correct inverse function also just by sketching this graph. Okay, so this would be open circle, come kind of down like that, and then the line negative x. Okay, so we could see that these two graphs, this is just a rough sketch, but these two graphs are actually reflections about the line y equals to x. Okay, last one. Okay, so our function g, let's go ahead and sketch this. Okay, so we'll look like the graph of 1 over x for x strictly less than 0, so it's just going to be this branch. And square root of x for x greater than or equal to 0. Okay, one-to-one function, it would pass the horizontal line test. Okay, looking at the y value, so for this first part, 1 over x, that will be y less than 0. And then y greater than or equal to 0 for the square root of x. Okay, so now for the first part, we switch the x and the y's. Okay, if I multiply both sides of the equation by y, I'll have y times x equals to 1, where then I can divide by x. And what do you know? We're back at y equals to 1 over x. This is going to be for x less than 0 and for y less than 0. Okay, looking here. For the second piece, okay, I'm going to square both sides of the equation to isolate y. It's going to be for x greater than or equal to 0, super important, right? X squared for all real numbers is not a one-to-one function. And then for y greater than or equal to 0. So G inverse will be 1 over x for x less than 0 and x squared for x greater than or equal to 0. Okay, the domain and the range are all real numbers for G, so they will be for G inverse as well. Okay, and we could also sketch G inverse. And for x less than, okay, so this would overlap. You can see, very rough sketch, but those two graphs would be reflections about the line y equals to x. Okay, on Friday, you guys, when you guys have your practice test, I will answer any and all questions on inverse functions. You guys will have some practice problems for homework, which you can start after watching this video. And just know that I will answer any questions that you guys have on inverse functions, and we can go back to examples in the notes if something wasn't clear. But again, just remember, we will talk about this on Friday, and then you'll have time to work on your practice test as well. I will not do a homework quiz on Friday. Instead, I'll have some sort of a warm-up that would have been similar to the homework quiz. Okay? See you then.